हेलो, am I audible? हेलो, मेरा आवाज सुनाई दे रहा है? हेलो, am I audible? Okay, so let's start today's class. So today we will be discussing spectral density. This is the topic for today. Spectral density. So there are two types of signals, as you have learned in your NPTEL course. There are two types of signals. One is an energy signal and another is a power signal. So in an energy signal, what is the identifier of an energy signal? That the energy is finite. Energy is finite. On the other hand, in a power signal, we have a finite power. So an energy signal is where the energy is finite, and in the power signal we have finite power. But in an energy signal the power is infinite, whereas in a power signal the energy is infinite. So in an energy signal energy is finite, power is infinite. Power signal power is finite, energy is infinite. So we define two types of spectral density now. Spectral density SD, let's call it SD. Okay, spectral density SD are of two types. For an energy signal we will have ESD, or energy spectral density. Similarly, when we have a power signal, when the signal is power signal, we will have a power spectral density. Power signal, we have power spectral density, which is henceforth called PSD. So these are the two quantities we will be dealing with today. One is ESD, one is PSD. When to apply ESD? When the signal is energy signal, or aperiodic. When to apply PSD? When the signal is a power signal or the signal is periodic. Okay. Any doubt at any point you can ask me. Just interact and ask. Okay, unmute your mic, ask the question at any point. Okay. So now we will go on to the definitions. So what is energy spectral density? It can be shown that energy spectral density is simply the Fourier transform XF modulus square. So mod XF square. That's it. That's the energy spectral density. You take the Fourier transform, you find the magnitude of it, you square it. That is the energy spectral density. Power spectral density is a bit more complicated. What is energy? What is power, I mean to say? Power is per unit energy. So energy divided by time is power. So in one sense, energy spectral density and power spectral density should also be similarly related, and they are. So mod xf square, but this time we will divide by the time period t, and we will take limit t tends to infinity. This is the power spectral density. Okay. So what does energy spectral density mean? Energy spectral density means energy per unit bandwidth. Okay. Whereas power spectral density means power per unit bandwidth. Say you transmit a sinusoid. Not a sinusoid. Sinusoid is not a good way. You transmit a signal that is band limited to signal that is band limited to band limited to say 100 hertz. Means the bandwidth of the signal is 100 hertz. The signal has 10 watt power. Then in power spectral density PSD is equal to 10 by 100 is equal to 0.1. What will be the unit? Watt per hertz. But usually we won't get questions in this format. Usually we have to do Fourier transforms and then take the square, like shown here. But this is the physical significance of PSD. Okay. Now we go to the questions. So this is assignment 3 corresponding to lectures 12 to 14. Means lecture 12, 13, 14 of the NPTEL course covering energy and power spectral density. Okay. So the first question is the ESD of convolution of two signals is always equal to the product of their individual ESDs. So ESD of the convolution of two signals. So you have two signals X1 and X2. The convolution of them is suppose xt. Okay, xt is equal to x1 t convolution x2 t. So now they are saying that the ESD of the convolution of two signals, that is the ESD of xt, is equal to the ESD of x1 into the ESD of x2. That is the proposition. So you have to say whether this proposition is true or false. You have xt, which is related as xt is equal to x1t convoluted with x2t. Okay. So you must have heard of this adage that convolution in time domain is what in frequency domain? Can you tell me what convolution in time domain is? What in frequency domain? Tell me. Anyone? Unmute your mic and tell fast. Oh, okay. Only you are there. Okay, fine. Can you tell me? Convolution in time domain means multiplication in frequency domain. So convolution in time domain will simply transform to multiplication in time frequency domain. So xt equal to x1t convolution x2t means xf is equal to x1f into x2f. Now, what is the ESD of xf? ESD of xt rather, ESD of xt. As we have discussed, the ESD of xt is mod xf square. Now, we know that xf is equal to x1f into x2f. So, mod x1f multiplied by x2f whole square. Now, you just break the multiplication. This will become mod x1f square multiplied with mod x2f square. ठीक है? तो ये ESD of xt हो जाएगा ESD, ये mod x1 x square क्या है? ESD of x1. So it will become ESD of x1 into ESD of x2. Bas, फिर the statement given is true. The correct answer is true. So question 1 solved. Question 1, the correct answer is true. Okay. Now, moving on to question number 2. ESD of an energy signal can be periodic. They are giving 3 statements. ESD of a power signal can be periodic. And ESD, PSD can be negative. Okay. Now, the thing about being periodic is if something is periodic, then it will be infinite. हम लोग periodic मतलब क्या? Usually दिखाता है sinusoid, sine. So if you take a sine function, you will see that it goes on and on and on. Or you take any other function. What is the definition of periodic function? Periodic function means something that repeats after a particular time period t. Okay, after a particular time period t, it will repeat. So xt plus t equal to xt for all t. So it will go on and on and on. So if it was finite in 0, if it had a finite value in 0, it has to have a finite value in capital T, because 0 and capital T are same. So if it has a finite value in capital T, then it has to have a finite value in 2t. And if it has a finite value in 2t, it has to have a finite value in 3t. So if it is finite at one point, it has to be finite at all points. So it will be, so the signal will always be finite. So it will always be there. So the signal will be, in effect, signal will be infinite in duration. The signal will go on and on and on. If it is there in 0, it should be there in t. If it is there in t, it should be there in 2t. Have you understood the logic? Is it more clear now? Can you hear me now properly? Can you hear me properly? Hello, can you hear me properly? सुनाई दे रहा है आवाज? अरे So in question number 2, any signal that is periodic will go on and on for infinite duration. So if it goes on and on for infinite duration, it will be it will have an infinite value. So the ESD cannot be infinite, because ESD of an energy signal. So the ESD of an energy signal must exist. So it has to be finite. So ESD of an energy signal cannot be periodic. Similarly, PSD of a power signal cannot be periodic, because ESD of an energy signal means the signal has finite energy, whereas the PSD of a power signal means the signal has a finite power. So both of them have to be finite. So 1 and 2 both are false. Now coming to 3, as you can see in the definition, that ESD is mod xf square. Mod square, so it definitely will always be positive. Whereas PSD is limit t tends to infinity 1 by t mod xt square, mod xf square. So both of them will have infinite, both of them will have positive values, because both of them are mod and then squared. So ESD and PSD both have to be positive. So ESD and PSD can never be negative. So 1, 2 and 3 all are false statements. So the correct answer is C. All 1, 2, 3 are false. So the correct answer is C. Okay. Next, coming to question number 3. PSD of an energy signal is always 0. Now, energy signal means, what is the power? The power does not exist. So the power, if the power is 0, then if the power is 0, then the power spectral density will always be 0. If power is 0, then power per unit bandwidth is also 0. So PSD of an energy signal will always be 0. So question number 3, the correct answer is 3. PSD of energy signal is always 0. Because an energy signal has 0 power. Because since energy signal has 0 power. As simple as that. So if power is 0, then power spectral density is of course always 0. Fine. Question number 4. In question number 4, the energy spectral density SF of rectangular T by dt. So pi here means rectangular function. Pi here means rectangular function. So pi of T by dt means the signal will be rectangular in the duration bt by 2 minus bt by 2 to bt by 2. This is the definition of rectangular T by. Now, the Fourier transform of rectangular is sinc. More specifically, the Fourier transform of rectangular T by dt is bt sinc fbt. Is bt sinc fbt. Now what they are saying? The energy spectral density. Now energy spectral density is simply the whole square. Sorry, this won't be equal to, this will be transformed. So if you do a Fourier transform of rectangular T by bt, you will get bt sinc fbt. So this is the Fourier transform, right? XF. So what is the ESD? ESD is mod XF square. So mod XF square. So you just take the mod square. And since bt sinc fbt is a real number, so mod anyways doesn't matter. So it will just be b square t square sinc square fbt. Okay, b square t square sinc square fbt. So it will be, correct answer will be none. D, because one is bt square, one is b square t square sinc square ft, another is bt square sinc square bft. All of them do not exactly match with our answer. So correct answer is none. Now, here we are saying find us for the signal ht equal to 2b by t square plus b square, find the ESD. So what are the steps of finding the ESD? You first find the Fourier transform and then you take the magnitude and then you square it. Okay, so moving on, as we have seen that the signal ht is 2b by t square plus b square. So we need to find the ESD of the signal. So first we need to find the Fourier transform, and the Fourier transform of, they have given one hint. The hint is very useful here. They are saying the Fourier transform of e to the power minus b mod t is 2b by omega square plus b square. 2b by omega square plus b square. Now, by the duality principle, the Fourier transform of 2b by t square plus b square will be 2 pi into e to the power minus b into mod omega. So this will be 2 pi into e to the power minus b 2 pi b mod f. Now that I am done with this, I will simply, this is the Fourier transform. So what will be the ESD? ESD will be the magnitude whole square. So mod xf square. So this will be 4 pi square e to the power minus 4 pi b mod f. As simple as that. So 4 pi square e to the power minus 4 b pi mod f. So the correct answer is option A, which is what we got. So this one is done. Next, the 99% bandwidth of a signal is defined to be the bandwidth such that 99% of its energy is contained within the band minus F99 to F99. Find F99 of the signal defined in question 5. So Ht equal to 2b by t square plus b square. They are asking us to find the 99% bandwidth. Just like the half power bandwidth is defined at where the 50% of power is contained, this is 99% bandwidth. So 99% bandwidth is so we have to find the energy in the band minus F99 to F99, and then we have to find the total energy, and the total, it should be 0.01 of the total energy. So to find the total energy, first we need to integrate the ESD. So what is the ESD? ESD is 4 pi square e to the power minus 4 pi b mod f. So to find the bandwidth, we need to first find the ESD. To get the ESD, we need to total energy. To get the total energy, we integrate over the whole frequency axis. So we will integrate over the whole frequency axis. Four pi square e to the power minus 4 pi b mod f df. So we are integrating this ESD over the whole frequency range. Now the thing is, um, ESD. Huh. Now the thing is, this is an even function, right? So this will simply be 2 times 0 to infinity 4 pi square e to the power. See, this is mod f. So f is within mod. So this is an even function. So if it is an even function, so we can simply put 2 into 4 pi square. So the negative and positive parts of integration will be same. Now you simply do 8 pi square x e to the power minus 4 pi b mod f by minus 4 pi b. So this will be 4, and with this is within the limit 0 to infinity. At infinity this will be 0. At 0 this will be 1. The exponential will be 1. So it will be 2 pi by b. So the negative signs cancel out. 4 pi and 8 pi square cancel to 2 pi. And finally the exponential part is 1. So 2 pi by b. Now we have to do another integration. This time such that we have to find what is F99, right? So we have to again find energy, but this time within the band minus F99 to F99. So energy in F99 band or 99% band. The energy in 99% band is minus F99 to F99 4 pi square e to the power minus 4 pi mod bf b mod f. Now this is of course another even function. So E99, that is the energy of the 99% bandwidth, is 2 into 0 to F99 4 pi square e to the power so this will become 2 pi by b into 1 minus e to the power minus 4 pi b mod f, rather df. The mod is not necessary because we are in the positive frequency region. Let's erase the mod here also. The mod is not required. And here also. Oops. Now, according to the question, E99 is 0.99 of totally, implies 2 pi by b 1 minus e to the power minus 4 pi bf is equal to 0.99 into 2 pi by b. So 2 pi by b, 2 pi by b cancels. 1 minus 0.99 is 0.01. So e to the power minus 4 pi bf is equal to 0.01. So f equal to ln 0.01 divided by 4 pi b minus 4 pi b. or you can just invert this. This will become ln 100 by 4 pi b. ln 100 by 4 pi b. The options are ln 10 by 4 pi b and ln 100 by 2 pi b. So none of these. The correct answer is ln 100 by 4 pi b. The correct answer is ln 100 by 4 pi b. Okay, so here we have seen that if we need to find the energy of a signal in any given bandwidth, at any given bandwidth, like from any frequency to any frequency, what we need to do is we need to integrate the EST between those two frequencies. So if you want to find the energy between frequencies f1 and f2, you simply integrate the EST between f1 and f2. Whereas when if you want to find the power of a signal between two portions of a signal, like between a bandwidth, particular band, then you simply integrate the PSD. So here, and what are the steps for finding ESD? You find the Fourier transform and then you find the Fourier transform and then you integrate it. Okay, so let's take a 5 minutes break here and then we will move on to question number 7, is it? Yeah, we will move on to question number 7. There will be a 5 minutes break. So if you are watching the recorded version, you may fast forward to 5 minutes.
Dubai.
Okay, uh, let's start the meeting again. So the next question is, Null bandwidth of a signal is defined to be the least frequency f naught such that sf not equal to 0, where sf is the energy spectral density or ESD of the signal. So wherever the ESD is 0, that frequency point is called the energy spectral density. So find the f naught for rectangular T by AT. So this will be question number 7. Yes. So question number 7. Rectangular, the time domain signal is given as rectangular T by AT, which means it will be there from minus AT by 2 to AT by 2. Okay, so xt is present in this domain. Now it is a well known fact that the rectangular function has a Fourier transform that is sinc. So AT sinc, no sorry, not AT, actually it will be T sinc FAT. So apologies, T sinc FAT. Now what is the ESD? ESD is T square sinc square FAT. Now find the point where ESD is 0. ESD f naught equal to 0. Find this f naught. That is the null bandwidth. So T square sinc square f naught AT is equal to 0. Since T is non-zero, then sinc has to be 0. Sinc f naught AT is 0. That is the only logical conclusion. So when is sinc 0? At n pi. So f naught AT equal to n pi, where n is an integer, implies n is an integer starting from 1, rather a natural number. So f naught is equal to n pi by 80. Now null bandwidth is least. Null bandwidth is defined as is least f naught. So the least value of frequency for which bandwidth is 0. So f naught is equal to pi by a t, where n equal to 1. So that is the minimum, pi by a t. So sorry, I have made one mistake. Sinc f naught AT. Okay, sinc here is not defined as sin x by x, but rather sin pi x by pi x. So implies sin pi f naught AT by pi f naught AT is equal to 0. Implies, therefore, here it is not defined as, sinc is defined in a different way, implies sin pi f naught AT by pi f naught AT equal to 0. So the denominator will go away and pi f naught AT will be equal to pi. Pi f naught AT will be equal to pi. Implies f naught AT will be 1 over 80. So the correct answer is 1 over 80 or option A. Now, coming to question 8. Consider a signal whose frequency response exists only for positive frequencies, that is, f greater than 0, and let the energy contained within the band 0 to f is given by EF. So, whose frequency response exists only for f greater than 0, so we don't have to integrate it f less than 0, and the energy is contained within the band 0 to f. So, the lower limit is 0 and the upper limit is f. And this energy is denoted by EF. Then, what is the energy spectral density? Okay, so over a bandwidth f, the frequency, the energy is given as EF. Over a bandwidth f, the energy is given as EF. So the energy spectral density, let's assume it to be SF. Let ESD be SF. Now, they are telling that there is a frequency f such that EF, let's denote this particular frequency by f naught to avoid confusion. So this particular frequency EF naught, the energy in the band 0 to f naught is given by EF naught, and that is SF naught, SF dF. So it is the EF is simply the integration. So for any general frequency, EF is SFDF, right? In an indefinite integral. So how do we get SF? We simply differentiate EF with respect to frequency. Simple. Okay. So differentiating EF. That is the correct answer. So the answer is option B. So this will not be question 9. This will be question 8. So the correct answer is option B, differentiating EF. Okay. Let's now go to question number 9. In question number 9, the energy contained within the band 0 to f, f greater than 0, EF is given by the following expression. Okay, so the energy EF is given, not the energy spectral density, but the energy EF. So now they are telling us to find SF. In the previous question only we derived SF equal to DEF DF. SF, question number 9, is equal to DDF of EF. So SF will be DDF of 1 by sigma cube A plus A sigma F plus sigma square A plus A sigma F plus sigma square F square all multiplied with an e to the power minus sigma F. So this becomes a simple problem of differentiation. So this is now just high school maths. So first, when you do derivative of product, you take the derivative of the first term, which is 1 plus the derivative of A will be 0 plus A sigma plus 2 sigma square F e to the power minus sigma F. And in the second part, you will take the derivative of e to the power minus sigma F, which will be minus sigma to the power minus sigma f, and then this whole thing, a plus a sigma f plus sigma square f square, done. And this will be okay. Let's not do this way. 1 by sigma cube let's take e to the power minus sigma f common, and what we are left with is a sigma plus 2 sigma square f plus a minus a sigma minus a sigma square f minus sigma cube f square. So a sigma will cancel. So it will be 2 sigma square f minus a sigma square minus sigma cube f square by sigma cube e to the power minus sigma f. Now you can take a sigma square common. So the final answer, take a sigma square common. So the final answer will be, cancel it, 2f so the final answer will be 2f minus a minus sigma f square whole into e to the power minus sigma f. This is the final answer. So let's match with our options. F square plus, okay, so first term is f square, and then there is a 2 minus a. So f into 2 minus a. So f square plus f into 2 minus a. But the thing is, there is a minus. So minus f square. So the correct form is none of them. None of these are correct. None of these match with the answer we have got. So the correct answer is D. None of these. Okay. Finally, autocorrelation function. What do we know about autocorrelation function? Okay. So we need to go a little bit onto the details of autocorrelation function. Okay. What is autocorrelation function? Autocorrelation function means how much the samples of a signal or the instances of a signal are correlated with each other. That is autocorrelation. So R x x tau is within the entire signal range, say 0 to infinity, xt and xt minus tau dt. So we are multiplying the signal with itself, but one of them is a normal version, one of them is a delayed version. Okay. So xt into xt minus tau. Now I have done this Rxx tau. Now there is a theorem called Wiener-Kirchner theorem. Okay. This states that Rxx tau, if you take the Fourier transform of that, you will get the energy spectral density, ESD, or power spectral density, ESD. Okay, so the spectral density is the Fourier transform of the autocorrelation function. Or conversely, we can say that the autocorrelation function is the inverse Fourier transform of the spectral density function. Okay, so this is the Wiener-Kirchner theorem. Now, the autocorrelation function is a Gaussian pulse. So, it is given as 1 by root 2 pi sigma e to the power minus t minus mu whole square by 2 sigma square. Okay, now they are saying that the autocorrelation, you have to directly find the autocorrelation. Okay, we don't need any spectral density here. We have to directly find the autocorrelation. So it's just a matter of integration. Anyways, those theorems are important, but otherwise this is just a matter of integration. So xt is the well-known Gaussian pulse, 1 by root 2 pi sigma e to the power minus x, or rather t, sorry, t minus mu whole square by 2 sigma square, well-known Gaussian integration. Now, what they're saying is that what they're asking is the correlation function. So Rx tau is the over the whole range. So here Gaussian is a two-sided function, right? Gaussian looks like this. Gaussian is a two-sided function. So it extends over the whole range of minus infinity to infinity. xt x t plus tau dt. Now, one by root 2 pi sigma e to the power minus t minus mu whole square, you multiply with 1 by root 2 pi sigma e to the power minus t plus tau minus mu whole square by 2 sigma square. Now, if there is an addition in exponential power, so we can say it's actually a multiplication. If the power is getting added, means the result is actually a multiplication. So root 2 pi sigma will become 2 pi sigma, and e to the power minus t minus mu whole square by 2 sigma square. This one we can break down as e to the power minus t minus mu whole square, and then there will be a tau square sigma by 2 sigma square, and then there will be a 2 tau into t minus mu. Okay, three parts will be there. So okay, so we will take all the t parts. We will take all the t parts here, and we will try to separate the t parts from the tau parts. Okay, so this will be t minus mu plus tau whole square. T minus mu is a, tau is b. So a plus b whole square is a square plus b square plus 2ab. So t minus mu whole square by 2 sigma square e to the power minus tau square by 2 sigma square, and another is e to the power minus 2 tau t minus mu by 2 sigma square dt. Now, we take the 1 by 2 pi sigma. Okay, Now to simplify things a bit, e to the power minus t minus mu whole square by sigma square. This will be the first term. The 2 is getting vanished because we are adding 2 of these things. So half plus half. Half plus half. And the e to the power minus tau square by 2 sigma square is a constant. So this will go out of integration. Okay. And then there is another part which is sigma square tau into t minus mu. Okay, 2 tau t minus mu by 2 sigma square. So tau into t minus mu. Now put t minus mu as p. Therefore, e to the power minus 2 tau square sigma square by 2 pi sigma. This thing is a constant, okay? And let's denote this constant by a k. So this integration becomes k dot exponential minus p square by sigma square minus t tau by sigma square. Now we will try to complete the square. Okay. So we will try to complete the square. This will become, let's conceptualize tau as 2 into tau by 2. So this will be dp. dp and dt are same. So minus p square by sigma square minus 2p tau by 2 by sigma square minus tau square by 4 sigma square. This I am adding to complete the square. So the next term will be plus tau square by 4 by sigma square. Next. Okay. So the integration will become k times minus infinity to infinity e to the power minus p minus tau by 2 whole square by sigma square plus tau square by 4 by sigma square. Okay. Plus na minus. This will also be minus because there is a minus overall. Now this p whole square, we have to bring this to a Gaussian format or else we cannot solve this. So we will take x minus tau square by 4 sigma square outside and we will expand the k. What was the k? K was e to the power minus 2 tau square sigma square minus 2 tau square by sigma square by 2 pi sigma. Okay. And this integration as you can see is vaguely Gaussian. We just need to do a few transformations to make it completely Gaussian. And then we can use the fact that the integration of Gaussian between minus infinity to infinity is 1. So now we have to make this 2 sigma square, right? So you just multiply by root 2. So can we write like this? 2 into sigma by root 2 whole square. Okay. And we will similarly, so we will just write like this, and we will take a root 2 pi sigma by root 2. So we will be effectively taking pi sigma inside the integral. The 2 will remain outside the integral. So here we can see it's 2 and this is 1 by 4. So these two powers are 2 and 1 by 4 of tau square sig by sigma square. So 2 plus 1 by 4 is 9 by 4. So 9 by 4. This thing is 9 by 4. And now there is a half below. Yes. Okay, so there is a half below. And when we use the okay, so there is a half below and we will take the pi sigma inside. Why? See, rather we will take a root pi sigma inside, not the whole thing. Why? Because we will do this. So there is a root pi sigma inside, so we can write it as root 2 pi sigma by root 2. So we are multiplying and dividing by root 2. Okay. And finally we have a Gaussian form. See, there is this is a Gaussian. The mean is tau by 2 and the variance is sigma by root 2. Now you may say, is this a standard Gaussian? No, this is a Gaussian with mean tau by 2 and standard deviation sigma by root 2. So finally this will, but even if the mean and standard deviation are not standard, they are not 0 and 1, the integration of a Gaussian is always 1 over the entire range. Because Gaussian is a PDF, right? Probability density function. So the integration of it over the entire range will be 1 because the integration of probability density function is 1. So this will all evaluate to 1. So e to the power minus 9 tau square by 4 sigma square, and then there will be by 1 by 2 root pi sigma, something like that. Okay. So this may not be, yes, 1 by 2 root pi sigma, and I might have 1 by 2 root pi sigma, the denominator is correct, but this exponential part I might have done a mistake somewhere because it is a very lengthy calculation. So ultimately you will get something like this. So e to the power minus some tau square by sigma square by 2 root pi sigma. So that is you are getting the correct form. We are getting the correct form. Denominator there is 2 root pi sigma, as you can see, 2 root pi sigma, and here it is 2 root pi sigma, not root pi whole root pi sigma, just root pi and then sigma. because we are taking the whole sigma inside, right? So it is 2 root pi sigma, and in the exponential I might have done some mistake there. So it is e to the power minus tau square by 4 sigma square, not 9 tau by 4 sigma square. So you can just cross check. You can do the integration again by yourself and check. Okay. So this will be option, the answer will be option D, none of these. Because the options given here are, see, one of them has 2 root pi, it is not correct. One of them has 2 root pi sigma square, that is also not correct. So even you don't need the exponential part. Just looking at the numerator part, you can see, denominator part, you can see that our answer is none of these, because ours is 2 root under pi into sigma. So none of them has 2 into root under pi into sigma. Option A is 2 into root under pi, B and C are 2 into root under pi into sigma square. So our answer will be answer D. Okay. The integration might have been a bit clumsy, so please recheck this calculation. Okay. If you have any doubt, you can ask me now, or you can ask in the NPTEL forum. Okay, there is a NPTEL forum, you can ask there. Now we will be happy to answer your queries. So any doubts? Okay. If you don't have any doubts, as I have completed the assignment, I will be ending the meeting today. The assignment and the recording of this solved session, problem solving session, will be available in the NPTEL website. Okay. Thank you. Have a nice day.